Here we have an optimization problem. It says find two numbers whose difference is 100 and whose product is minimum. So whenever you read an optimization problem like that, you need to figure out few things. What do we need to find? We need to find two numbers. We don't know their names, so let's name them X and Y. What is the condition? Condition is that their difference should be 100. What do you need to optimize? What do you need to optimize? We need to optimize their product. We want that to be minimum. Okay, product is X times Y. Now use the conditions to bring our product to single variable, right? So we can say that Y is equal to X minus 100 from here. You see, Y goes on the other side, 100 goes on this side. So we have this. That means my product is equal to X times, in place of Y, I can put X minus 100. Now, once I have that, we can distribute it inside before. You guys can notice that my product, which I want to optimize, meaning minimize, is a single variable function. So that I can name as my function. My function is the thing which we need to optimize. So we have to make it single variable using our condition, which we did. So this is our function. We want to find the minimum value of this, and we want to find two numbers which make it minimum. So now our calculus starts. We need to find the derivative of this function. The derivative would be 2x minus 100. We need to find critical points. Critical points are when f prime x is 0 or f prime x does not exist. Now, this function is a polynomial, so f prime x always exists, so that's not a problem. We only need to put 2x minus 100 as 0. 2x is 100 and x is 50. So 50 is our critical point. Now to check if at 50 our function is minimum or not, we can use second derivative test. For second derivative test, we need to differentiate this first derivative and find second derivative. The derivative of this is 2. Okay. Now, second derivative at 50 is positive. Actually, this second derivative is always positive. So the graph is always concave upwards, right? So because the second derivative is positive, we can claim f is minimum at x is equal to 50. Now notice f here is product. So basically product is minimum at x is equal to 50. We needed to find x. That part is done. We also need to find y. Y is equal to what? X minus 100. So your answer should be for y 50 minus 100. The answer is negative 50. So our final answer, we have x is equal to 50 and y is equal to negative 50 is such that the product is minimum. And you can also say the minimum value of the product should be equal to x times y, meaning 50 times negative 50, negative 2500. Let's do another problem. In this question, we have find two positive numbers. So this kind of gives us two things. It tells us what we need to find. We need to find two numbers and also gives us condition. Both of them should be positive. Okay. Whose product is 100. That is another condition. XY equal to 100. These all are conditions. This is what we need to find. Whose sum is minimum. So what we need to optimize. Optimize here is to minimize, is the sum. So sum should be equal to what? Sum of these two numbers should be equal to x plus y. Using the condition, we can find that y is equal to 100 by x. We put that here in place of y. That means my x plus in place of y is 100 by x. This is the sum I need to minimize. Once I get it into one variable thing, I can name this f of x. This is what I need to minimize. Once I have a function which is a single variable, I can apply my calculus. What is my calculus? I find first derivative of the function. I can also write this as x plus 100 times x to the power negative 1. So derivative of x is 1 plus, when negative 1 comes down, negative 100 times x to the power negative 1 negative 1. So 1 minus 100 by x. Okay, let's write it one more time. 100 times x to the power negative 2. That also can be written as 1 minus 100 by x square. That is my first derivative. I can make the common denominator here. So that would be x square minus 100. The second step is to find critical points. Critical points are given by either when f prime x is 0 or when f prime x does not exist. Now, f prime x is 0. F prime x is a fraction. F prime x is 0 if the numerator is 0. So x square minus 100 is equal to 0. F prime x, because it's a fraction, it does not exist if denominator is 0. So it will not exist if the denominator becomes 0. So from here, we can get x square is equal to 100 and x is equal to plus minus square root of 100, which will give me plus minus 10. But you guys remember the condition, we have to have positive numbers. So we will not take negative 10, we will only take x as 10. And x does not exist when x is equal to 0. We can't even take that because the product is 100. So these both numbers are strictly positive. This also cannot be taken. Only critical value which we can take is 10, because the 0 does not satisfy the feasibility condition, right? Because the product has to be 100. If one of them is 0, the product will not be 0. Now all we have left to do is to check that the sum is minimum at x is equal to 10. How do we do that? For that, we are going to use second derivative test. For second derivative test, I am going to use my first derivative and differentiate it one more time to find second derivative. Derivative of 1 is 0 minus 100 times negative 2 will become 200 x to the power negative 2 minus 1. Basically 200 times x to the power negative 3, 200 by x cube. That is my second derivative. If I put this critical value in second derivative, 200 by 10 cube, I don't know what that value is because I'm not calculating. All I need to check is that it is positive. If this is positive, we can say this is positive for sure, right? There's no negative sign there. So we can say f of x is minimum at x is equal to 10. What was f of x again? It was sum. So we can say sum is minimum at x is equal to 10. We also need to find y. Y is equal to 100 by x, 100 by 10. The answer is 10. So answer is x is equal to 10 and y is equal to 10, and the minimum sum is equal to what? 10 plus 10, 20, when the product is 100. That is your final answer.